Now, I have to prove theorem 2. What does theorem 2 say? Theorem 2 says that if the chain is positive recurrent, then then there exists a solution to pi is equal to pi p, right. So, given the irreducible DTMC is positive recurrent. Okay. So, therefore, I can take expected Tjj is finite for all j, right, because I am given that it is positive recurrent. Now, I have to show that pi is equal to pi p has a solution. What we will show pi j is equal to 1 over expected Tjj for j belongs to S satisfies star, i.e. We should have sum over pi j equal to 1 and sum over j pi j p j I is equal to pi I. This is what star is, right. So, what am I doing? I am proposing a solution, right, 1 over expected Tjj. I mean, this I know from the, this is what I know to expect, right. I am just simply going to show that this satisfies the balance equation. Okay. Now, I just have to show that I proposed a solution, I just have to show that these two solutions, these two equations are valid. Okay. Now, let me first show that, right. Let me show this is 3, let me just show that is 4. Okay. So, we will use renewal reward theory. Okay. Consider the process njj of t, okay, starting at state j, and I am going to count the number of times I hit state I, okay, in each renewal interval. Okay. See, I know now that see, I am given in theorem 2, I am given that the chain is positive recurrent. So, I know that njjt is a renewal process. Okay. So, let Ri of t. So, I am going to define a reward process which is 1 when state is equal to I. Okay. Then I know that one over t integral 0 to t Ri of t dt is equal to expected Ri, which is the expected number of times I will be in state I between successive visits to state j over expected Tjj. Okay. So, this is almost surely, this is by renewal reward. I think we already saw this equation, right. So, if you look at this, this is the fraction of time spent in state I, right, and this we already know to be equal to what? So, if you look at the process nji of t, right, it will be the by strong law for the delay renewal processes, we can say that this is equal to 1 over expected tii, right. So, I have 1 over expected tii is equal to expected ri over expected tjj, correct. So, this expected ri is what? So, this implies, let me just write down, expected ri is therefore equal to expected tjj over expected tii, which is simply pi I over pi j, right. So, expected Ri is the expected number of visits to I between successive returns to j. Okay. So, expected Ri, I am going to call it, I am going to denote it by rho I of j. Okay. This is going to be useful later. So, this is good. Expected number of visits to I between returns to j satisfies pi I over pi j. Okay. Now, what is sum over I belongs to S expected Ri, right. So, let me write. So, this is I am essentially trying to sum, I am trying to show that sum over pi I is equal to 1, all right. So, I am just going to go back to this this equation. So, expected Ri, this expected number of visits to I between successive returns to j, right. So, if you look at this process j, 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 how many times do I hit I, all right. Now, if I take sum over I belongs to S Ri, right, that will be equal to the number of returns to state I plus the number of returns to state k. So, number of visits to state k plus number of returns to state L and so on, right. So, I am summing over all the states, I am going to number of visits to all the states, right, between visits to j. Okay, I am going to sum this over all j. Since the all I, sorry. So, this has to be equal to tjj, right, because the process has to visit some state or the other, right. So, this implies expected sum over I belongs to S Ri, which is equal to expected tjj. Okay. So, if you are willing to move this expectation inside this infinite summation, which is justified by dominated convergence theorem, okay, then you can argue that sum over I expected Ri. Expected Ri is the expected number of visits to I between successive visits to j. If you sum it over all states, this has to be equal to expected Tjj, right, which means that if I go back, so I know this. So, I know sum over pi I, which is just sum over I belongs to S 1 over expected Tii is equal to sum over I belongs to S expected Ri over expected Tjj, right, but sum over expected Ri is simply expected Tjj. So, that is equal to 1, alright. So, we have shown that sum over pi I is equal to 1. So, this is 3 is shown. Okay. Next, I want to show 4, right. Next, want to show 4. Okay. This 4 is saying that sum over pi j Pji is equal to pi I. Okay. The proof is somewhat similar. I will just indicate the reward process that we use. So, let me call this rj arrow I. Okay. So, reward process whenever the chain transitions from j to I. Okay. So, now I am going to let us say look at state I. Okay, I am going to look at I, okay, and I am going to look at a reward which is 1 whenever I have a transition from j to I. Okay. So, so if I look at this process NII of t, okay, so this transition may go from k to I, this transition may go from j to I. Okay. So, in this case I will accumulate one reward, here I will not accumulate any reward, right, only when I go from j to I do I accumulate a reward. Okay. Now, if you look at this again, right, if you look at sum over r j arrow I, sum over j belongs to S, this will be equal to 1, right, in each renewal interval. That why? Because the before you hit I in each renewal interval, you have to transition from some j or the other, right. So, again I can argue that sum over j belongs to S expected r j arrow I is equal to 1. Okay. This is again I am pushing the expectation inside the sum and all that, which is justified. Okay. Now, but what is the average rate at which this reward occurs? Okay. This rate of this reward, time average reward rate, equals so I have to be in state j and then make a transition from j to I. Okay. Now, what is the time average reward rate? It is the time average rate of being in state j and then making a transition from j to I. So, what is the time average fraction state j? 1 over expected Tjj, right. Then I have to make a transition from j to I, the probability of which is Pji. but since I have taken 1 over expected Tjj as pi j, this will simply be pi j Pji. Okay. This is the time average reward rate. Okay. This is nothing but for the renewal process NII, this is expected Rj to I transition over expected TII, right. This is just by renewal reward theory, right. This is nothing but if you take this guy here, I should write this as pi I expected R j to I. Okay. So, I have the expected reward for a transition from I over a renewal interval for a reward transition from j to I is simply pi j Pji over pi I. But I know that if I sum this over j belongs to S, I have expected Rj to I, this must be equal to 1, right. This is because of that. That must be equal to sum over j belongs to S pi j Pji over pi I, implies pi I is equal to sum over j belongs to S pi j Pji. Okay. So, we have shown 4 also. Okay. So, we have proved theorem 2. What have we proved? So, given a positive recurrent irreducible DTMC, I know that expected Tjj is finite. I have shown that 1 over expected Tjj, you call that pi j, satisfies the balance equations. Alright. So, whenever you have a positive recurrent Markov chain, 1 over expected Tjj has the interpretation of this stationary probability in terms of time average occupancy of state j. Okay. So, to summarize, so far we have shown that given first theorem 1 showed that if pi is equal to pi p has a probability distribution solution, then that chain is automatically positive recurrent. So, if by some means you manage to find a solution to pi equal to pi p, then that chain is positive recurrent. The solution you found is unique in the sense that the pi j will be equal to 1 over expected Tjj. Okay. And conversely, if the chain is recurrent, positive recurrent, then 1 over expected Tjj has the interpretation of the solution to pi is equal to pi p. Okay. Throughout, we have interpreted pi j as time average occupancy of state j so far. Okay. So, that is true regardless of any considerations of periodicity. Okay. Now, I want to briefly look at let me say this. So far, pi j which is just 1 over expected Tjj has the interpretation of time average occupancy of state j. Okay. Now, I am not just satisfied with the fraction of time spent in state j, I want to know if I run the Markov chain for a very long time, do I have convergence of the probability of being in state j to be equal to pi j, right. That I have not shown so far, I mean that I have not even talked about. Everything I have done so far is time averages. I have only used time average renewal reward process, right. I have just said if the state j is positive recurrent is equivalent to saying that 1 over expected Tjj which is pi j is a solution to pi is equal to pi p, and therefore, pi j has the interpretation of the fraction of time spent in state j. Okay. What about question? What about long term behavior, right. So, can I talk about things like if I start in any state I, can I say that limit n tending to infinity pi j n is equal to pi j? Big question mark, right. It is not at all clear that this can be done. Okay. So, that is what we will address next. Steady state interpretation. So, we are going to now interpret pi j as a steady state probability, not just a fraction of time, okay, spent in state j. So, this pi j, you know, it is on the one hand it is a stationary distribution. So, you start in pi j, you remain in pi j, all right. Also, because of renewal reward theory, we have shown that pi j has the interpretation of the average fraction of time spent in state j. Now, I am going to go into a different interpretation, which is the steady state interpretation. Can I say that no matter where I start, the probability that I will be in state j after a very long time n approaches pi j? Can I say that? Answer is not always, but sometimes in some nice cases you can say this, and we are going to use Blackwell's theorem, again from renewal theory, right. Now we have to have periodicity considerations, okay. So, because if you have a periodic chain, then you may not have convergence of Pij, okay. Suppose we have a DTMC which is irreducible, and positive recurrent. Okay, let me look at this renewal process of returning to J. Okay. If state J is periodic with period D, then NJJT, see this, if you are saying that returns to J can only occur at multiples of J, I am saying that if J is periodic with period D, we are saying the returns to J can occur only at multiples of D, right. Then NJJT is a renewal process, of course, renewal process of span D is an arithmetic renewal process. All the arithmetic renewal process. It is an arithmetic renewal process of span D because all the returns to state J only occur in multiples of times D, right. Now, recall Blackwell. Theorem for arithmetic renewal process of span D it just says that let us say n of t is an arithmetic renewal process of span D. Then we have expected number of renewals n of n of t plus k d minus n of t plus, also maybe I should write it as n of k d minus n of k minus 1 d, all right, is the which is the probability of renewal at t is equal to k d is nothing but d over expectation of x, where x is the the renewal distribution. This we know from Blackwell. Okay. So, for this Markov chain, so apply this to NJJT, right, which is an arithmetic renewal process of span D. We have probability of renewal at time t is equal to k d. So, this is of course, this is as limit. So, this is not for all k, right, this is as limit k tending to infinity. So, limit, so everywhere I should have limit k tending to infinity, here also I should have limit k tending to infinity. This is equal to limit k tending to infinity p j j at time k d, right. This I can say is d over expectation of t j j, all right. This is by Blackwell. Now, you say if the chain is aperiodic, of course, in addition to being irreducible and positive recurrent. So, if you have a countable state DTMC which is irreducible, positive recurrent and aperiodic, then that is just d equal to 1, is not it. So, I can write limit k tending to infinity. Now, you have a arithmetic renewal process of span 1, right. The span d is simply 1 now, right. So, this is k tending to infinity p j j of k, right. So, this is the k step transition probability of. So, starting at j, what is the probability that I will be in j after time k, and I am looking at this after a very long time. This is equal to 1 over expected t j j, which is simply pi j, right. So, given that I start at j, the probability that I file myself at j after a very long time is by Blackwell pi j, okay, which means that I have this interpretation of finding myself, this pi j is steady state interpretation is valid, but this is only for starting state j. What about limit k tending to infinity p I j k? Okay, we can consider you are starting at I, then I am looking at returns to j, right. So, you can look at the delayed renewal process, you can look at the delayed renewal process n I j of t and apply Blackwell. Okay. So, remember that there is a corresponding Blackwell's theorem even for delayed renewal processes. Okay. Let me just find it for you. This is theorem 583 in Gallagher. Okay. You can do that and say that limit n tending to infinity n tending to infinity sorry k tending to infinity p I j k is equal to 1 over expected t j j, which is equal to pi j for any state I. Okay. So, now because of Blackwell, thanks to Blackwell, I have an interpretation of Pij k after a very long time k. No matter where I start, right, the probability I find myself in state j after a very long time is equal to pi j. Okay, as limit k tending to infinity, Pij k step transition probability is equal to pi j. Okay, this is from Blackwell. So, you can see how powerful some of these renewal results are. Renewal reward theory was heavily used. Now, we are using the powerful Blackwell's theorem to give Pij k to show that Pij k has a limit as k tends to infinity for a aperiodic Markov chain, and pi j has the interpretation as the limit of Pij k, right, as k tends to infinity. So, this is quite powerful, as you can see. The renewal theory, renewal reward theory, and Blackwell's theorem, and it helps us derive these fundamental results about countable state DTMCs. All right. Of course, this is not the only way to show these long term properties. We have taken the approach of renewal processes. There are other approaches as well. For example, there is an approach of constructing the steady state probabilities pi j directly by looking at the expected number of visits to a state I between successive visits to state j. Maybe I will briefly mention that a little bit later, but this is one valid way to approach it. There are other ways to approach these Markov chains as well. Okay, I will stop here.